Hello, my friends. Our next little installment here deals with two-dimensional motion. This is a good time to talk about the vector. Now, in our last one, we talked about vector quantities, things like displacement, velocity, acceleration. We'll introduce some new ones like force. That's a big one. Those are the big ones that we draw. The biggest ones we draw are these. We can represent any of these things like that. Okay? We call this the tail. We call this the tip. All right? This vector has things that are called components. If this is a vector, let's just call it vector A. We can draw this component and call it AX. And we can draw this component and call it AY. If there's an angle there, theta, you should be able to prove to yourself. I'm not going to go through the derivation because it's, well, simple stuff. But at this point, if you don't know it, just memorize that. Well, excuse me, don't memorize it. It's right in the reference table. If you want to find the horizontal component of a vector, it's the magnitude of the whole vector times the cosine of the angle that it's at. Similarly, if you want to find the vertical component, it's A times the sine of theta. And what's A again? So, if this is, I don't know, if this is 20 somethings and this is 30 degrees, well, your AX would be 20 times the cosine of 30. So that's 20 cos 30, 17.3, whatever it is. Meters per second, newtons, meters, whatever. And this would be 10 of those things. Okay, make sure that's a must. Got to be able to do that. All right, and so what we're saying is that a displacement can have, part of it go this way and part of it go this way. Or a force could pull something, some amount to the side and some amount upward. A velocity can have part of it that goes west and part of it that goes north. So there can be elements of quantities that happen in two different directions. Hence, this is called two-dimensional motion. We apply this the most to things like projectiles. Okay? Two big kinds. First, the horizontally launched. It does that. Oops, it travels downward some and has some vertical displacement that we can call dy. It has some horizontal displacement that we can call dx. It has some initial velocity that is in only the horizontal direction. So this is something about horizontally. Okay? First of all, maybe not first of all, but if we took this ball and dropped it from the same exact height that this one was thrown or launched or fired horizontally from, one big deal, same time in the air. And why is that? Well, because for the projectile one, here's what we would do. Never mind. Sorry. Here's what we would do for the projectile one. Make a little chart. So you have two different. So you make sure you keep directions separate. The big deal for a horizontally fired thing, you got to know that. That's the key to your salvation. The initial vertical velocity is 0. Look at the initial velocity. It's all horizontal. There's none of it that's up and down. Okay? We also know there's some dy. We also know that A is g. Those are both downward. Right? We have this Vx. Well, what we would do here is say, okay, if I know this, and I know this, and they told me this, what I could do is say, well, d is VIT plus 1/2 AY t squared. Well, VIY is 0, right? So that means that dy, which presumably they've told me, is 1/2 g t squared. You can find the time in the air, well, by doing 2 dy over g. All right, and we would do the same exact thing for this one. Dropped for us means, well, vi is 0, right? And, well, a is g. And it has the same dy. So we'd say d is vit plus 1/2 gt squared. And vi is 0. And the same t, right? T is the square root of 2t over g. Notice I'm not using x's and y's here because this thing is, the dropped one only goes in one direction. It goes straight down. The one that's thrown horizontally goes in two directions, but the vertical direction is the same exact thing. All this stuff is the same exact as that stuff. But the whole time that it's in the air, it happens to be moving horizontally. So how far does it go horizontally? Well, how far does it go horizontally? That's dx. It's just dx times t. So whatever you get here for time, that can go in there. Okay? So that's a big one to be able to do. The other one, the other projectile is this one, the one that's shot at an angle at some speed vi, and it goes like that. Here's an angle theta. Okay? Remember a couple of big things. Acceleration is g. Always. Everywhere. Only. Ever. It's g. It's g. It's g. It's g. Even at the very top, it's still accelerating downward. There's no horizontal acceleration at all. So that's one big thing. Here's one. Here's two. Vx is constant. It has a constant horizontal velocity, which says that there's no horizontal acceleration because there's no horizontal force. All right? Three things they'll ask you about. To make it go the highest it possibly can, make theta 90 degrees. Duh, shoot it straight up. To have it spend the longest time in the air, shoot it straight up. Duh. And to make it go the farthest dx, that is, theta equals 45 degrees. All right? If that's a surprise to you, I'm sorry. That's the answer. Okay? So that's some projectile stuff. Okay. That's it, folks. Thank you. We'll come back soon.